Hello everyone, good to see you all again. I'm just going to open up my laptop here as we go. So, as we had last time, these daily, just a second, let me turn this thing off. Right, as we did last time, what we'll always do is we will have this daily live stream where I'll just talk about anything that people are curious about. I do want to try to make sure that we balance the difficulty level a little bit better this time though, because I saw the feedback last time that some people felt maybe it was a bit too hard. Again, the objective of these daily live streams is to try to make sure that we can help as many people as possible to see that math is interesting. So even if you ask me a question that's about more complicated math, I'll choose to answer it if I think I can improvise a lesson that might make sense, even for people who are just starting out. Now, what I'd like to do this time is I'd like to also do a poll. I see that there are 85 people watching right now. If you can maybe write into the chat of what kind of math you're actually learning right now, this will help me a lot. I'll take a look at the chat and that'll give me an idea of what balance we have in this room at this moment. At the same time, I'll also start our own recording devices because we will be able to keep this for the future too. Hey Vivian, could you help me press the red button on the camera over there? It would work. We have help from our team here in the office. Yeah, the red button please, go ahead. Great, and let's see what we got here. Okay, I see that we have people who are studying algebra. We got a 3rd grade student in here. Wow, you're pretty advanced. Calculus, functions, AMC 10, 12. I see, so I can see where we are. We have a balance, and I will see that we have quite a few people here who are doing algebra or geometry. Some are algebra too, a few calculus. So I'll say my preference for questions today would be questions that are still around the geometry or Algebra 1, maybe something in Algebra 2. And of course, if you have questions that have to do with math competitions, that's totally fine too. In fact, I personally think that the questions in AMC 8s or AMC 10s are very interesting, and oftentimes you don't really need that much advanced math to try to figure them out. Oh, okay. I see a first question has come already. I saw your talk about the dice rolling. What is true randomness? That is a good philosophical question. You see, if you use a computer to generate a random number, I'm going to burst your bubble. It's not a random number. What the computer does is that it has something called a seed. That's like the last number you may have generated. And the way it gets the next number is it does a certain kind of arithmetic calculation to it that makes it look very random. I'll give you an example, just because we're talking about this right now. And I should also say, for anyone who's new to this daily live stream, I'm improvising all of these lessons based on just my own life experience. And so sometimes I'm going to tell you things that you might not really see written in textbooks. That's not because textbooks are bad. It's just because textbooks are showing you maybe the most efficient way to get something done. And here, we're doing storytelling too. So I was myself kind of curious about random numbers a long time ago too, and I was curious what computers do. This is not what they do, but this is a simplified version of what you could do to get a random number. Watch. Let's suppose I want to get random numbers between 0 and 100. Get random numbers from 0 to 100. And here, I want to say, I also want to allow you to get 0 as a random number and also get 100 as a random number. The technical word for that is the word inclusive. So whenever you see a problem that says, something from something number to some other number inclusive, it means including the endpoints. Here's a question. Does anyone in this audience know why I chose 0 to 100 inclusive instead of 1 to 100 inclusive? This is like a tricky question, which I don't actually expect anyone in the chat to know. But there is a good reason why I want to go from 0 to 100 for what I'm about to talk about, which is like how to get random numbers. What do we have here? Aha! Somebody said there's 101 numbers. So that is useful, okay? From 0 to 100 inclusive, there are 101 numbers. Now, 101 is more special than 100. If I was talking about trying to find the numbers from 1 to 100 inclusive, there are 100 numbers. Why in the world might I prefer to generate random numbers if there are 101 numbers that I could choose from instead of 100? Does anyone know anything interesting about 101 that is not true about 100? It's prime. Exactly. So we're going to do something involving prime numbers for which it will be very useful that 101 is prime. 101 here is a prime number. Prime means that if I try to divide it by anything, I'll always have a remainder. It won't divide cleanly unless I divide by 1 or itself. That's 101. Now here's what I'll do. Let's show how you can make a sequence of numbers that looks kind of random. What I'll do is I'll say, here, someone give me a random number. Somebody give me a number between 0 and 100 inclusive. That's an integer, a whole number. Anyone, give me a number between 0 and 100 inclusive. I'll take the first one I see. I'm watching your comments to see what comes. 42! Oh my gosh, that's not a random number. Come on, guys. That is the answer to the universe. But that's okay. If you don't get that reference, there's a book called Hitchhiker's Guide to the Galaxy, and 42 is the magical number. But okay, I got 42. And now here's what I'm going to do. I'm going to always take the number I have so far, and I'll always add something to it, and then multiply the result by something. But it's always going to be the same, okay? So what I'm going to do is I'm always going to do plus, I don't know, I'm choosing some random stuff, plus 3, and then I will multiply by 7. Why not? Those are two crazy numbers, but that'll be enough to do something interesting. Help. What's 42 plus 3? That one I think I could even do. 42 plus 3 is 45. Okay? Right? So let's see. So we got 45. And what's 45 times 7? Now I have to do some actual work. 45 times 7. 7 times 5 is 35. What do we have here? 7 times 4, 28 plus 3. Did I do that right? 315. Let me tell you, I hate doing arithmetic. So whenever I do a problem like this, I even go and look at it and I say, can I think of a good reason why I know that's right? I'm going to give you a magic trick. If I look at that number, 315, what I say is 315 is a multiple of 9. There's something that we teach in the daily challenge class of one moment. Hey everybody. Is everyone back? Let's see. So let's double check. Do we have sound? Can we do a sound check, please? Are people able to hear me? If so, please put inside here that says it's back. It's back. Okay, excellent, excellent. Yeah, I should say, because I'm now doing these live streams like every day, we in fact run out of batteries faster. So thank you everyone for commenting that the sound was off. Again, this is an informal chat. I hope that you can see that, actually everyone has these random issues come up as well. And now I also know I got to make sure that I got a battery charger in the office. Let's continue. Back to this thing, which is the 315. How do I feel comfortable that 315 is the right answer? Well, 315 I saw was a multiple of 9. And we teach this in our daily challenge number theory class, and I'm sure you've learned elsewhere. Maybe you've learned elsewhere. I shouldn't say I'm sure you have. But you may have learned elsewhere that a number is divisible by 9 exactly when the sum of its digits is divisible by 9. And this 315, 3 plus 1 plus 5, is 9. And so 315 is divisible by 9. Now, why might I use that to double check my multiplication? Does anyone know why I know the answer should be divisible by 9? Why is the answer supposed to be divisible by 9? I see. We have maybe slow mode here in the sense that the comments don't come right away, but I just want to let people be able to say, exactly, 45 is divisible by 9, and so the answer should be divisible by 9. Excellent. That helps me double check my calculation. I'm telling you this trick because whenever you do a multiplication problem, it's very easy to just mess up by forgetting to carry, and that usually makes your answer be off on one digit, where you're off by 1. And this check lets you quickly find out if you're off by 1. Because if you kind of add up the digits, if it added up to 8, you'd be like, oh, there's a mistake. Okay, let's continue with these random numbers. For anyone who joined late, what we're talking about is somebody asked, how do you generate truly random numbers? And I decided to answer their question by telling you how to generate not random numbers that look random, but that's similar to what a computer is doing. So back to this thing, I said, let's generate numbers from 0 to 100 inclusive. And I'll do that by starting with any old number you chose. People chose the most fancy number, 42. And then I say what I'll always do is I will add 3 and then multiply by 7. And what I get is 315. But I can't say that 315 is a number from 0 to 100 inclusive. On the other hand, what I can do is I can say, what would happen if I divide 315 by 101 and look at the remainder? So there's a word for this. It's called remainder. When you divide by 101. Actually, the word for it is called remainder modulo 101. But I'm just going to write some symbols just to say I should divide by 101 and look at the remainder. What's the remainder if you divide 315 by 101? Does anyone know? Let's see. Yes, I see people said mod 350 divided by 101. It's actually not that hard. I like 101 because it's nice to divide by 101. Yes, the answer is 12. And that's because 315 divided by 101, well, 303 is a multiple of 101, right? And so 315 minus the 303 would give me 12. So my next number is 12. Okay? Let's do it again. So 12 looks like, random number has appeared. Let's do it again. What's 12 plus 3, everybody? 15. And then I should times 7. What's 15 times 7? Oh, let's use the blue to do all this drawing. 15 times 7. Well, this is another nice product. 7 times 5 is 35. Let's make that clean. It's 35. I see some people are already doing this so much faster than me. 105. By the way, 105 is 3 times 5 times 7. That's 15 times 7. The more of these math problems you do, the more often you recognize numbers like this. Okay, and what happens if I divide by 101 and take the remainder? I get 4. Oops. Whoa, let's clean that off. Okay, that's 4. Let's just keep doing this a few more times. What happens if I do 4 plus 3? 4 plus 3 is 7. 7 times 7 is 49. And 49, when I divide by 101, leaves a remainder of just 49. By now you have seen that the numbers I'm getting are actually not always even numbers. I'm able to flip over to odd numbers. And in fact, if somebody gave you a sequence of numbers, 42, 12, 4, 49, it would look, sort of random. And in fact, a computer does something similar to this. It does some kind of a calculation, and in the end, it does something where it divides by some prime number, and in the end, you're able to get a sequence of numbers that looks pretty random. And in fact, for your video games or anything else that you're using random numbers for, it works quite well. I'll tell you a story of when it doesn't work. So I actually used to think, why not just use the computers to make random numbers? I used to write computer games for fun. I would write video games for other people to play. And when you're writing a video game for people to play, sometimes you've got like some enemy which is moving around, going left or right, and it has to decide whether to go left or right. You could be like flipping a coin. So when you write a computer program, you're often able to get a random number. And if you get the random number, you're able to take a random number. It's a random number between, with like a random whole number, random integer. And one way to decide whether or not the bad guy should go to the left or to the right would be to say, is the random number, well, does anyone have an idea? If the computer gave you a random number, which it said was random, and it was a whole number between 0 and like 4 billion, what would you do? If you knew the computer was going to give you a random number between 0 and 4 billion, that's a whole number, and half the time you're supposed to make the boss go left, left for you guys, and half the time make the boss go right, what might you do if you had some whole number between like 1 and a billion and 4 billion? Yes, even or odd. That's exactly what I always did. And this worked for video games when I was writing video games. It was like, yeah, great, the boss is kind of like wandering around like this. Then at some later point in my life, I became a mathematics researcher, and I was in fact working at Microsoft Research in Redmond, Washington, and I was trying to make a computer simulation to go and test how a certain randomized computer algorithm would work. And I did the same thing. I used the computer to generate random numbers, and I needed to do coin flips. So I just said, is it even or odd? And the computer behaved really weird. It gave me long, strange patterns in the evenness or oddness. Now, the situation is that the reason why this is dangerous is because if you look at all the things that we're doing here, we're doing some kind of arithmetic, and we're doing it modulo some prime number. And in fact, there's going to be a repeating pattern. And in fact, if you do something like this, you will get a repeating pattern, and the repeating pattern will happen even faster if you happen to be doing things with just even or odd. So what I'm trying to tell you is that if you ever want to generate a random number, if you ever want to generate a random coin flip, do not do what I did. What I did was check whether the number is even or odd. The reason that's dangerous is because all this stuff is with remainders and arithmetic anyway. The correct way to generate to generate a heads or tails, like random outcome, if you're going to get a number from 0 to 4 billion, from 1 to 4 billion, is you should say, is the number less than 2 billion or bigger than 2 billion? That's a tip for all of you guys in case someday you ever go into simulations or computer science. It is better to take the computer random number and split it between less than half or more than half of its range. That is better than looking at whether it's even or odd. And I ran into very weird results for my computer simulations when I did even or odd. So I'm just sharing with you, this tip. Hopefully it will save you someday. Finally, to answer the question you actually asked, how do you generate a truly random number? Well, we don't really know. In the sense, when I say we don't really know, we believe that quantum mechanics, which is like an area of physics, tells you certain things are uncertain. And so some people think that you can generate random numbers by like looking at atmospheric patterns or wind speeds or something which is actually physical. It's like if you have inside your chip, you're measuring vibrations of tiny things inside the chip. In my understanding, the way to get a random number is to use something physical. And if all you're doing is using your computer random number generator, it's usually doing something like this, unless your computer is equipped with some other chip that actually uses the physical world around us. So next time you actually want to get a random number, well, just grab a coin and you flip it. That's also physical. Okay, that was a pretty interesting question. Thank you for asking. As you can see, if you have joined this live stream a bit later, the whole point is that we're not trying to just efficiently do one problem. I'm trying to do some storytelling. I'm trying to show you how the math all fits together. I'm trying to show you how it fits together with things you might even touch later in your life. And my preference is to hit questions that I can talk about for as many people to understand as possible. Okay, now we're going to roll into another question. Angles of a triangle are an arithmetic progression. Side length relationship. So this is an interesting question. Someone wants to know if I happen to have a triangle. Now we're in geometry. Actually, I'm curious about the answer, so let's find out. In geometry, we can sometimes have triangles. I'll draw one of these, like one of my favorite triangles. One of my favorite triangles looks like this. This, we draw a little, like, it looks like a square because that represents 90 degrees. Okay, 90 degrees, and that's because in a full rotation, you get 360 degrees. Now, 90 degrees is a quarter rotation. Does anyone know what triangle I've drawn? I mean, if you like geometry, this doesn't quite look like a 45, 45, 90. Yes, I see. Learning Math with Miguel says it's a 30 degrees, 60 degrees, 90 degrees right triangle. And I don't promise it's exactly 30, 60, 90. I just tried to kind of freehand it, but I intended for it to be 30, 60, 90. And the question that was asked was, what's the relationship between the side lengths, or is there any? Well, let's see. Oh yeah, you also said arithmetic progression. Not everyone here has heard of what an arithmetic progression is, but it's very easy to understand. You see, they are 30, 60, and 90. Can anyone put into the chat what the relationship between like this sequence, like what's so special about 30, 60, and 90? It's a progression, so there's something about the order seems to be beautiful. It is 1:2:3, that is true, but there are more arithmetic progressions in the world. If I wanted to give you 30, 60, 90, 120, that's also an arithmetic progression. And it's also an arithmetic progression if I put a 0. Now maybe you can see, arithmetic progression means you add 30 each time. That's right. So the angles we're looking at are these 30, 60, 90, the ones in the middle. And indeed, as people have said, they are where you add, they are where you add 30 each time. Plus 30 and plus 30. Okay. And the person who asked the question was curious. Will there be any relationship between these three side lengths? Well, let's see. I drew the 30, 60, 90 because it's famous. In a 30, 60, 90 triangle, the relationship between the three sides can be found. I'm going to review why this is true. I don't like to just tell you a fact. This can be found by drawing another triangle, which is the mirror image of it when I flip down. Watch. I'll do this. I'll do this. And I drew another 30, 60, 90 right triangle. But now what have I actually drawn? What's the whole thing? What's the whole thing that I've drawn? It's an equilateral triangle. All three sides are the same length. And so the 30, 60, 90 is half of an equilateral triangle. If that's the case, I can start telling you something about the relationship between the lengths on this triangle. I would need to put some length down first. Oh, I don't know. What if we make the length of this side 1? Well, I don't like that. And the reason I don't like that is because I'm about to have to tell you how long this side is, that little bit, that half of the long side. So 1 is inconvenient. What would be a nicer number? I'm just looking for the relationship between the three sides. I can choose any length I want. 1 is inconvenient because I have to divide it by 2. So if I have to divide it by 2, can anyone tell me a better length to pick for that long side? 2. Yes. You could also use 40 billion, but then my numbers would just be too big. So that's why we choose like the first nice number. Okay. If that's 2, this part is 1. This part is also 1, but we don't care. Okay. Now, can anyone tell me how you would figure out this length right here? I happen to have a right triangle. And if I draw the right triangle looks like this. There's a 2 and there's a 1. I would use the Pythagorean theorem. Right. And again, this is something which I should say, if you're curious about the proof, I personally prefer to show the proof when I use it, but we don't have time in the daily live streams. Actually, I'll say that's the free preview lesson on the daily challenge. So it's in fact free. The very first day, what is it, module 0, day 1, that's the free preview. So if you're curious, you can see a complete proof of the Pythagorean theorem there. That's free. So now let's see what we can do here. Pythagorean theorem, I need to know what goes here. You use the fact that the sum of the squares of the sides of this, this side squared plus this side squared equals that side squared. And so because of that, you know, if we gave it some name, I'll do this slowly just because not that hard, but we'll do it slowly. If I call that a and I don't know what it is, the Pythagorean theorem tells me that if I just go and take a squared, let's see, do I have enough space? Let's do it here. A squared plus b squared, that's the 1 squared, is supposed to be equal to 2 squared. So can anyone tell me what a squared is? This is not bad. 2 squared minus 1 is 3. So a is the square root of 3. Okay, good. So we have now figured out that for this particular triangle, whose sides are in arithmetic progression, whose angles are in arithmetic progression, this particular triangle has sides in the ratio 1, square root 3, and 2. Is that nice? Unfortunately, there's not really a nice pattern here at all. Now, if I want to compare to another triangle, what else could we do? I guess I could tell you another triangle whose angles are in arithmetic progression. By the way, if I want to make 3 numbers in arithmetic progression that are the angles of a triangle, does anyone know what the middle one has to be? I like how somebody is like, yeah, the ratio, is that nice? I don't know. I don't know if this is actually nice. We'll see. So let's see. If I take any other triangle, if I want 3 angles in arithmetic progression, what should the middle one be? Yes, I see people said 60 already. Because you see the sum of the 3 angles in a triangle is equal to 180. And so the average of those 3 angles has to be 60. And the average is the one that goes in the middle. Oh, I want the 60 to look nicer. That didn't look nicer. Let's go again. 60. Okay. So if I want to make now 3 more angles in arithmetic progression, I could put 60 in the middle. What else should I put? I'm going to put 60 and 60. Just because that one I can do very easily. If I do 60, 60, 60, well, that's just an equilateral triangle. If they're all 60, 60, 60, well, all those are the same. And so I'd say, yes, if those 3 are in arithmetic progression, not only could it be this 1, square root 3, and 2, it could also be 1, 1, 1. Doesn't really look like there's a good pattern. So I'll say it doesn't look good. Now, my answer to your question then would be, not much, you can't say much. Unless you've taken Algebra 2 or Geometry. And what I'll say is that there is actually something I can tell you about this. But this is going to be a little bit more complicated and will probably not make as much sense to people who haven't seen something called sine before. So now, sine is a trigonometric function. I saw somebody was like, what about 20, 60, 100? Well, hold your thought. Let's put that here. 20, 60, 100. Hey, you know what? Since you said that, I want to do that. I want to do that triangle. So let me try to draw that. And I'm telling you the key is that there's a special function. It's a trigonometric function called sine. And at this point, I'm going to try to do this explanation really fast because I understand that for people who haven't learned this before, it doesn't make much sense anyway. For people who have learned this before, this should be a review. Okay, so what would happen? Let's go and try to draw what would it look like, 20, 60, 100. 100 is more than 90, so that triangle should be a little bit more than a 90, like this. And 20 is a pretty small angle, so maybe it looks like this. Let's pretend that is 20, 60, 100. Oh, and by the way, it sort of looks right because this part looks like it was part of an equilateral triangle. It's just that weird stuff happened over here. Okay? So I've got 20, I've got 60, 100. And now, since this part is directed at people who kind of know what this sine is talking about, why did I say sine? Let's suppose I give one of these sides a length. Suppose I give I don't know, what should we call 1? The shortest one. Let's call this 1. If I call this 1, does anyone know what I would use that involves the word sine to try to figure out the other sides? And indeed, sine is the opposite over the hypotenuse. But again, I'll say I'm just doing this part fast because I know that for people who haven't studied this before, I cannot possibly teach you the whole concept in like 5 minutes. So we're just going to do this part quick. But I want to use the all caps 9th life says law of sines. And the law of sines, which is actually not that hard to prove, but we won't do it today, tells me that if I have, let's give these some names. Let's call this A, let's call this B. That looks like a weird B. Here's a B, okay? The law of sines tells you that if you take the opposite over the sine of the angle that is opposite, so a side divided by the angle is opposite, is equal to A over sine 60. And that tells me immediately what A is. So A is equal to sine 20 divided by sine 60. No, it isn't. No, it isn't. That's a mistake. Please catch me whenever I do something like that. A is equal to the other way around. Sine 60 over sine 20. Okay? So that's A. How about B? Maybe you can see what it is. Let's do the same thing again. Let's use a different color. 1 over sine 20 is equal to B over sine 100. And so in that case, yes, what is sine? I'll say I apologize. This part is an explanation that will take less than 3 more minutes, and it's directed at people who have taken Algebra 2. But we'll get back to things that are understandable to everyone in a bit, just because this question had popped up. And so what B is sine 100 over sine 20. Okay, so now I can tell you about your triangle. Your triangle is 1, and then over on this side, which is opposite the 60, it's sine 60 over sine 20. The B side is equal to sine 100 over sine 20. Can anyone tell me a different way to write 1 that makes this look like a pattern? I see somebody asked, what's the point of sine then? The point of sine is you can do calculations like this. In fact, we are about to find out the relationship between the 3 side lengths, and it turns out to use sine, and that's why this concept is so important, and that's why it's useful for learning later. 1 is 1 out of 1, but I want to have a pattern. Yes, I want to use sine 20 over sine 20. What that means is if I take this triangle, and I look at the ratio between the 3 sides, I could draw you another triangle, which is just a scaled version of it. Let's rescale the triangle, same angles. Okay, I know I drew it the same size, but let's pretend it was like scaled, okay? Same 3 angles, 100, 60, and 20. But if I scale the 3 sides, sorry, keep the angles the same. If I scale the 3 sides, can you tell me something nice I could write about like the 3 sides? I don't want to call the 3 sides sine 60 over sine 20, and sine 20 over sine 20, and sine 100 over sine 20. Is there something else I could write that would still be in the same ratio? Well, I could multiply everything by sine 20. So this would be sine 60. This would be sine 20. And this would be sine 100. So maybe, multiply all by sine 20. Thank you very much. Good observations. So indeed, there is a relationship. Even though I said, I don't see any pattern, put the angles in arithmetic progression, what in the world should happen to the sides? Doesn't look like there's any pattern because we got like a 1, root 3, and 2. Well, it turns out there is. It turns out that the relationship between the 3 sides is you take the sines of those angles. So even though the angles themselves are in arithmetic progression, the sines of them are not. However, if you just take sine of each of them, well, that happens to be the ratio of the 3 sides. So this is related to this Algebra 2 topic, and at this point, hopefully you see that it would be useful to learn about this sine thing someday. Nice question, by the way. I'll tell you, I didn't know the answer when I started doing the question for you just now. I was like, I wonder what it is. And, to me, the fun part about doing these daily live streams is it's like, I have to do math too, right? It's like, what is this? Okay, great. If you can't understand anything, I'm sorry. This particular part was Algebra 2. Let's roll back down to something that maybe is more approachable. So I'll say, I saw that there was one question called how to solve two equations and two variables. I want to say that one is the kind of explanation that, I could give. But I actually think your teacher probably can also give that very, very well, and there isn't as much of a story I can tell you about that one. So what I'll say is, I would encourage you, let's hold that type of question away. I want to talk about these questions which maybe are, still interesting to people who are learning Algebra 1, but at the same time where we can talk about something which might be interesting that's outside your book. Because you already have a great teacher at school who can tell you about that. What do we have here? Yes, you're right, I am the teacher. I am a teacher, but my opinion is that I want to use my time to try to give you the kinds of things that are weird, the kinds of things that are hard to find in other ways, because there are a lot of good teachers in the world already. I'm honored that you would be interested in me explaining this to you. Okay, let's see. Okay. What do we have here? I'm just looking at all of these different questions that are coming about. I also saw another question coming in saying, like, how do you attempt proofs, like on the USA JMO? My answer to you on that is, if you're asking those kinds of questions, please come on the weekends, because we'll hit that one really hard there. I'll give you a very quick answer right now, which is the same way you just saw me do this problem. I didn't have a clue what the answer was. On the other hand, if you saw, I tried a few small examples first. And this is what you should do whenever you're trying to find out something in general. It's like, I don't know what the answer is. Do some examples. And after you see some examples, you find out, no nice pattern. And at the same time, you should always be thinking in the back of your head, do I know anything that can relate areas of math with the problem I'm doing? And that's how I ultimately came up with this sign approach. Oh my gosh, what equations can model coronavirus? Now that's interesting. Let me see if I can take that one. What equations can model coronavirus? So let me start with the simplest equation. The simplest equation to model coronavirus is called, how long does it take for the number of cases to double? Now, why would the number of cases double? Let me explain. So the deal is, at the very beginning, I'm going to try to draw something on this board. Let's hope it makes some sense. At the very beginning, we have a lot of people. Here are all these people. We'll use white dots. There's nothing wrong with them. These people are going to fill up my screen. All these people. This is like people in the world. Okay? Now, if you have all of these people who are normal, what happens is that at some point, someone gets sick, like this person. And if that person gets sick, usually what happens is people have like a daily life where everybody in their day is going to talk to a certain number of people. These days, we're trying to reduce those numbers dramatically. But look what happens. If that person is usually going to talk to some other people, well, then that person might get 2 other people infected. By the way, if that person only gets 1 person infected before that person is cured, then it is not an epidemic. You may have seen in the news, some people are talking about this thing called R0. R0 is talking about, if you got infected, about how many other people do you infect. And you may have seen something in the news saying, we want to get R0 to be less than 1. We would like to make it so that every infected person makes like only 0.9 other people on average infected. That would be great, because then the number of infected people would reduce. Because it's like, well, if at this point I have 1,000 people infected, at some point they get better or possibly, unfortunately, pass away. But these 1,000 people will infect 0.9 times 1,000, which is 900 people. And now you've got these 900 people spreading the infection. I'm simplifying everything. But like 900 people, after they infect other people, they'll infect 810 other people. And the whole thing will start decreasing and decreasing and decreasing. Okay, but if R0 is bigger than 1, you have a problem. Because then what happens here is that this person might infect these 2 people. Oops, let me use the proper purple, pinkish purple. Now we've got 2 more people infected. What I drew here has those people getting infected far away from that person. In real life, they actually might be closer together. Well, these days they might be. But let's just say a week ago or a month ago, they might be all over the place. Like you might have taken the subway in New York City and you infected somebody else while taking a subway ride. And suddenly the person who was in the Bronx who got infected is now infecting somebody who lives in Manhattan and something like that. But now what happens is that this person, the very first person, is sort of done. But each of those 2 people in their lifestyle infects 2 more people. So, for example, maybe this person infects these 2 people, and maybe this person infects these 2 people. And as you can see, what's going on is that as this is happening, the number of people who are being infected is starting to grow. How is it growing? Let's draw a little chart. So, I guess let's make a chart. Day. I'm going to make a simplification. Let's pretend that every day is when this cycle changes. In reality, it's not every day. It's every certain, like maybe 14 days. I don't actually know what it is for the coronavirus. But let's suppose on day 1, the number of people who are, let's call it contagious, is 1. I have 3 columns here because the third column is going to be how many people are, just a second, how many people contagious, and the third column is how many people have ever been infected. Okay? So ever been infected is also 1, obviously. Now, what happens on day 2? On day 2, can anyone tell me how many people are now contagious? Well, maybe I want to make a bit more clear what I'm doing. Remember what happened is that on day 1, we had that one person who was contagious, and then we're actually saying that person doesn't become contagious anymore. They're sort of done. And then there are these 2 other people who are now contagious. So that's what my model is saying. There are now 2 people who are contagious, and the number of people who have ever been infected, what is that? What do you see? If I had 1 who was ever infected, and now I have 2 more who are contagious, the total number is not 2. The total number is the original 1 plus the 2 more, and that's 3. 1 plus 2 is 3. Now what happens on day 3? Help me out here. How many people are contagious now? Well, those 2 people were contagious. They're not anymore. The original 1, not anymore. But those 2 people each made 2 more people contagious. So it became 4. There are now 4 people who are contagious. And how many people in total have ever been infected? Well, we had 3 at the beginning. Not at the beginning. We had 3 just now. And then if you go and add 4 more, you get 7. Okay? 7. Excellent. I see 7. You see some powers of 2. It is pretty interesting. We're adding up powers of 2. 4. So then it's 1, 2, 4, 8. Ever infected. Instead of 7, 7 plus 8 is 15. Does anyone see an interesting pattern about what's going on this right-hand side, this ever infected? 1, 3, 7, 15. What do you see? Are those powers of 2? Well, not quite powers of 2, but they're very close to powers of 2. In fact, if you look at the column in the middle, what you see is that it looks like they're just off by 1 from powers of 2. They're not quite 2n plus 1. 2n plus 1 would be like the odd numbers. Instead, they're sort of like 2 to the power n minus 1, right? If in general I had a day n, okay, how many people are contagious on day n? You would write that as a power of 2, but it's 2 to the power n minus 1. How do I know that? Well, I just use the fact that I see a pattern, right? I often like to look at a long list and then go and say, well, what should the pattern be? And it happens to be 2 to the n minus 1. And the ever infected, it also is 2 to the n, but the number ever infected is 2 to the n and then minus 1. Okay, so this is how you can see that you actually can model the number of people who have ever been infected by a virus by something like this. This is called an exponential function. So it's called exponential because you're taking the exponent. You're putting n in the exponent. In general, this is an exponential function. So oftentimes people will go and try to model growth of things by the exponential. And you may have seen in the news a lot of newspapers with these graphs of cases where they try to graph it exponentially. I will say you cannot actually model completely that way because you see the exponential function just keeps getting bigger and bigger. What happens if the exponential function gets bigger than the total number of people in the entire world? Well, that couldn't possibly be. It couldn't be that someday the number of cases of coronavirus was 50 trillion. There aren't enough people in the world for that. And then why is that? So why is this a bad model? Well, when I say bad model, the model works well as long as the number of people who are infected so far is not so big. When I say not so big, I mean it's not occupying all of the dots in this picture. However, at some point, when somebody is trying to infect someone else, it's like you've already been infected. Maybe you're either immune or unfortunately you've passed away. For example, what happens if this particular person over here tries to infect this person as one of the two? Well, nothing would happen. So what happens is as the number of people who are infected rises so much that the fraction of people infected is pretty big, then this starts to happen. And the way to think about this is, if you look at a picture, which is like the fraction of people infected ever, let's draw this graph. So let's call it the fraction of people ever infected. And this is time. I guess we can draw a little arrow here too, but that won't be so important. Because does anyone know what's the biggest possible fraction you could have of people infected? What fraction of people infected is the biggest, meaning like everyone got infected? Well, that's the fraction called 1. It's just like 1 over 1. We often just call it 1, okay? Oh, I saw somebody asked, what time does this live stream end? Unfortunately, this live stream ends at 3:30, I think, because today we started at 2:30. So yesterday was 2 to 3, today is 2:30 to 3:30, and we will try different hours as we keep going through the week. But the biggest fraction is 1. We call it just 1 over here. So you cannot have the fraction of people who are infected to go above this. Well, at the very beginning, you should see something that's growing exponentially, meaning that it should look something like this. This is like exponential growth. But then as it keeps growing exponentially, what happens is that at some point, the fraction of people infected, I don't know, maybe it's like 20%. Then as these people are infecting other people, kind of 20% of the time when the infection is trying to spread, it doesn't spread. So the deal is like somehow here was somebody who was infected. On average, they infect 2 other people. But actually at this point, 20% of all the people are untouchable. So if you were going to infect 2 people and 20% of them are untouchable, you will only infect 80% of the 2 people. You will on average only infect 1.6 other people. This is actually an important calculation. I actually want to write that down. I want to say that, if each person typically infects 2 others, then if 20% of people, let's call it PPL people, are already, let's call it out. Out means, unfortunately, either immune or passed away. Okay, so out means not possible to get infected anymore. Then if 20% of people are already out, let's write an R, are already out, then each person actually infects about, what was the calculation I did? The calculation I did was to say, you typically infect 2 others, but 20% of that doesn't cause infection. So what would I multiply by what to find out how many a person would typically infect? This is actually quite interesting. It tells you the relationship between this R0 number and like how deep an epidemic spreads. 1.6 people. And how you get 1.6 people is you do the calculation of, well, it was supposed to be 2, but 20% of them are already infected and does nothing. So what's left for your actual infection? It's what's left from 100% when you take out 20%, which is 80%. 80% of 2, which is 1.6. Okay? And what you're seeing then is that the rate of growth of this exponential starts to slow down. In fact, it starts to slow down, and you will even see what we call an inflection point. Sometimes you'll see this word in newspapers, inflection point. Inflection point is when something changes from kind of growing fast to kind of growing not as fast. Okay, well, actually that's a very bad way to explain it. What I should really say is inflection point is when something changes from a curve that looks like it's growing faster and faster, where the speed of growth is increasing, to a curve where the speed of growth is decreasing. It can still be growing, but at least the speed of growth is decreasing. That's a good situation to be in. This is related to acceleration as well. Okay, so we have this inflection point, it kind of slows down, and as a bigger percentage of people gets infected, it really slows down. By the way, once you manage to make it so that each person typically infects only one other person, well then you're basically not going to have the epidemic spread anymore. Does that make sense? You're sort of like, at this point the epidemic starts to die down. Like as soon as each person gets only 0.9 new people sick, then there won't be that many more people getting sick. So can anyone tell me the break-even point? Break-even point meaning, at what percent of total population infection does it make it so that each person typically infects only one other person? Do you see what's going on here? It's like we're saying typically you infect 2 other people. If 20% of all people have already been infected, that's my graph here, ever been infected, then typically a person infects 1.6 other people. I see people said 50% infected. At 50% infected, so let's draw another picture. Not another picture, let's draw a line. This is 50%. Pretend that's straight and pretend that's parallel. At 50% infected, then I should actually start to see the whole thing peter off. And that's what you'll see. I massively simplified the model, by the way. I should say that this is just trying to be as easy to understand as possible to people who are even learning algebra. But I'm trying to show you that's the relationship between this number here, which we call R0, which you see all over the news. That's the relationship between that number and typically what we might be able to expect in a very simplified model of how many people will get sick. This is also why, even if you have a very contagious epidemic, it somehow isn't necessarily true that every single person is going to get it. Because once enough people have gotten it, then the epidemic doesn't propagate because the person that's getting other people sick is just getting like immune people sick, and that doesn't do anything. So the kind of graphs that you see are exactly what you see over here whenever you model these kinds of diseases. And I hope this also helped to explain a little bit of the news that you're looking at these days. Let's take some more questions. What else can... Oh yes, I see somebody said 2 horizontal asymptotes. We could say so. We could say that somehow there's one horizontal asymptote which is at the height that it would reach. And there's another horizontal asymptote, you could call it, which is at the x-axis, which is that, we started at nothing. Okay, I want to do one thing before I take the next question, I want to do 2 things. I'm going to take a sip of water because it's important to protect your health. And as a tip for coronavirus, try to keep your throat not completely dry because then that helps to, your natural body things help to protect. And the second thing is you may notice that sometimes I point at the screen. The way I do that, if you're ever curious how I film these lessons, it's just the same way the weather person does it on TV station. Actually, this screen behind me is just green. It's using a green screen. I have some computer set up which is doing all of this stuff. And what I get to look at is exactly what a weather person looks at in front of me, which is a screen that shows me what I look like to you. Except that screen just went on screensaver. So I'm going to type in that password now, and I will be right back in approximately 30 seconds. Maybe that was faster than 30 seconds. But a note to self, note to anyone else doing live streams, make sure screensaver is turned off. All right, let's take some more questions. So today, let's see, what would be pretty good? Okay, gosh, I see, I'm going to say a few things. If I see a question, I might address it, but I might not necessarily answer it. Can I explain how the shoelace theorem works? Yes, the way it works is you should remember to always tie your shoes when you go outside. Oh, I think that's not what you were looking for. There is some theorem to find the area of a polygon in the plane. Sorry, if you draw a polygon, you can do the area just using the coordinates. I will say that's very interesting. If you want to know how the proof of that works, the way to do it is with something called mathematical induction, where you go and take smaller versions of your shape, and you actually end up building your shape out of triangles. So I'll say, I don't want to go too deep into that one here because I feel that would be maybe too advanced for this audience. But it shows the value of something called mathematical induction, where I kind of build up a more complicated thing from a simpler thing. What else can we see here? Oh, That's an interesting question. Well, so again, I'm going to say with all these questions here, I'm going to still be a little bit careful because I want to avoid things that might have something to do with algebra 2, if at all possible. Someone asked, why is there a sine of 0 when no triangle has a 0-degree angle? I'll just say the answer because not everyone knows what sine means. The reason is because sine is useful for more than just measuring triangles. It's actually, the neat thing about math is you can define these functions, like on your calculator. You can press the sign, you can put anything in it. In fact, you should have asked me, why do we have sine of 50 million? Like, that's a better question. It's like, you could take sine of 50 million. You can go take your calculator, type 50 million, press the sine button, you get an answer. I'll tell you why. It's because the most pure sound wave that you can make, I'll draw some sound wave picture, and now this will be hopefully understandable to lots of people. It doesn't have to use this trigonometry at all, but you may or may not have seen people draw sound waves that look like this. Have people seen pictures like this before? You don't have to have taken advanced math. In fact, you really just have to have recorded some audio before on your computer and kind of try to edit the sound. And what sound is actually just vibration. So in fact, what your ears are measuring is that the air that's coming into your ears has some vibrations going on it. It's actually compressing and expanding. This is also, by the way, when you have a gigantic explosion, there's a big sound because you have compressed air. The air is moving. Okay, but what this is showing is it's showing a repeating pattern. In fact, when you sing a note, the note is just like one constant frequency. That's actually what it's called. It's just one constant sound, one constant level of pitch, of highness or lowness. And the sine wave is actually used to model these kinds of not just model. The sine wave is actually one of the simplest pure sounds that you can have. And so if you ask me, why is there sine of 0? Well, the reason there's sine of 50 million is because if you graph sine, and you're going to say what happens 50 million steps along this line, you would still want to know what is the sine of that. The sine is very important because it turns out that all of the stuff that we do, like with the music that we listen to, we actually often compress music into some simpler, smaller files. You may have seen files called .mp3 or .aac. All of these are music files where I'm not actually storing all of the details of all of the wiggliness. Instead, what I'm actually doing, what most computers are doing, is they're sort of storing instructions that say, that sound you're hearing is made up of some simpler waves, kind of at the same time. You could imagine this if you were if you were Beethoven trying to compose Beethoven's Ninth Symphony. Did he have 9 symphonies? I think so. Beethoven's Ninth. Oh yeah, that was one of the most famous ones. Actually, somebody told me once that's why a compact disc has its length of an hour 15 to 20 minutes, and that's an hour and 15 to an hour and 20 minutes because that's what you needed to put Beethoven's Ninth. Unfortunately, a lot of our audience might not remember what a compact disc is anymore, but well, anyway, I grew up with those. But anyway, with these science, like with mathematics, you can actually decompose any complicated sound wave into actually a combination of these. And if you're curious how sometimes singers of songs that you listen to like on the radio, how is their pitch perfect? How are they able to sing exactly the right note, exactly high enough, exactly low enough? Sometimes they're using something called auto-tune. I'm not sure if you've heard of this thing before. It's like you can sing and it kind of makes your pitch sound like what it's supposed to be. And what's going on is that the computer is listening to the complicated sound wave of your voice. It's breaking it apart, roughly speaking, into waves like this. And it's taking those waves and trying to match their frequencies, like how quickly they wave, so that it matches a particular type of note. So, right, so I would say that's why you have sine of 50 million or sine of 0. It's so that you can do things like this. Okay, I see somebody says that somebody else uses auto-tune. Yes, actually many singers do. Okay, so let's see, what can I do? What can I do here? We've got about 2 minutes left. Oh, I'm trying to think of one that might actually be useful to do this. I'm looking at all of these questions here. How can one stop talking? I don't know, but if you tried to stop talking, I wouldn't be able to answer any of your questions after this. I'm going to just answer one question, which is quick. I say, why is algebra worth studying? I'm Kyle. Do you remember me? Yes, hi. Nice to see you again, Kyle. Why should you study algebra was the question? Is that right? Actually, I was busy saying your name is Kyle. I remember you. I forgot the question. Yes, why is algebra worth studying? Let's finish that off with today. Well, it's because algebra lets you have a language of doing math. So you see, if we were talking about like how do you model this growth, if I wasn't able to write down something like 2 to the power n, we would have no hope. In fact, if you look at what mathematicians used to do a long time ago, before algebra, before they could even write things down, I found this out when I was looking at the history of quadratic equations. As you know, I had something to do with that. And so if you look at this history of quadratic equations, back in like the 1600s, people didn't necessarily write down x. They didn't write all this stuff out. They wrote it with words. Imagine if what you're reading is something that says an unknown minus twice itself. Imagine if all the math you read looked like that. It would be horrible. You wouldn't actually be able to do anything. I know this because I was the moderator for the countdown round at the Texas State Math Counts competition last year, which was the final round for this math tournament in the United States. And at that competition, they give every countdown round moderator the problems, but the problems are all written like this because they want to make it so even if you don't know the math symbols, you can still read the problem. There's only one issue. I wanted to solve the problems too. You know, like, I want to play, but all these people, like the contestants, the students, they were able to see the problem on screen. And so they were able to just like solve it. And for me, I was looking at this nonsense and I was like, what is the problem? I don't even understand it because it's all written in these words. So back to this thing about why the algebra was invented. Oh, I know what this is. X minus 2x. Bam! That's minus x. So efficient. Algebra gives you a system of ways to kind of manipulate and simplify, where you can just look at things and use rules that are consistent and efficient. Now, algebra starts with Algebra 1, where you do simple calculations. Goes to Algebra 2, where you learn how to solve more complicated equations, and you even learn about other things like logarithms. But all of this stuff is invented so you can have a good way to try to solve all of these questions instead of staring at these kinds of words and having your brain unable to solve the problem. So with that, I will say that sort of unfortunately brings our time together somewhat to an end. I will, of course, be back again tomorrow. If you liked what you saw today, please do try to tell more people. The way that I'm making this decision of like whether or not to keep running here every day is directly related to whether or not there are enough people who feel like they're getting something out of it. And feel free to, of course, give us feedback. You can always message us. On the Daily Challenge website, we have our contact. It's actually support@poshenloh.com. If you contact us, we're always happy to hear feedback. And we want to make these as effective as possible. So again, thank you to everyone coming. I see 140 people as of this moment. I wish you all the best in this difficult season and have a great day.